Objectively, there may be a discrepancy between what we think of as sustainability as opposed to what the data tell us. As an example, a recent study looking at perceived versus actual sustainability of different beverage containers found that in regards to several different factors of sustainability, a certain portion of those who completed the questionnaire found that their perceptions of glass sustainability as a beverage container were higher than it actually was. To avoid this same mistake, we should utilize available sources and methods for determining and comparing the sustainability of products so that we can form a clearer picture of what affects sustainability. One of these methods is ReCiPe2016. But I always like to start definitions of an acronym with the words that comprise it, but for the life of me, I can't figure out what ReCiPe stands for. So this was what I wrote until about 10 hours into my research, I finally found in the original paper the origin of the term recipe, which I actually really like. You see, the creation of the term is multi-layered. On one hand, it's the amalgam of the Dutch institutions that oversaw its development. Radboud University in Nijmegen and the Rijksinstituut voor Volksgezondheid in Melu, basically the National Institute for Public Health and Environmentalism, Centrum Milieukunde Leiden, and pre-consultants. And for the second layer, we'll get to that momentarily. 2016's version was an update to the original in 2008, and the goal of this methodology is to quantitatively assess the results of a life cycle analysis. Quick recap from my other video, life cycle analysis is a way to measure the overall environmental impact of a product, such as a glass bottle, considering its entire life, beginning with the resource extraction process, continuing through to production and distribution, and finishing with where the product ends up. There are two main parts to a life cycle analysis: the life cycle inventory, in which raw data is gathered on a product's environmental impacts, and then the life cycle impact assessment, where the data from the inventory is then analyzed to determine the overall impact of the product on the environment. This second part is where the recipe methodology comes in, and it's also where we get the second layer of meaning I mentioned before. It describes the methodology's approach to the impact assessment as a comprehensive recipe for quantifying how a product's creation, use, and disposal lead to impacts on the environment. As you can imagine, the scope of a methodology such as this would be quite large in order to encompass all the environmental impacts one product might have. Or maybe it's not easy to imagine. Before I dived into this research myself, I overvalued a product's recyclability when considering how environmentally friendly it was. So to form a more holistic view of a product's impact, here are 18 factors to consider according to the recipe methodology. So each of these factors has a measurable aspect that is a conversion of the data collected in the first phase of the life cycle analysis, the life cycle inventory. Most of these are equivalents of a standardized value, meaning they aren't the levels measured in the inventory, but instead are converted into units that can be better compared to other impact assessment results. See if you notice 2 or 3 themes as we move through each of them. PM2.5 refers to tiny particles or droplets in the air that are 2 1/2 microns or less in width, according to a New York government health website. According to the same website, the width of the larger particles in the PM2.5 size range would be about 30 times smaller than that of a human hair. The X here would be a number, typically a 2, for nitric oxide, which in the atmosphere can be a precursor to ozone. The troposphere refers to the atmosphere surrounding us and most of our activities, including planes. While ozone is good in other atmospheric levels, its excess creation in the air we breathe is attributed to respiratory disease incidence as well as species loss, which is why this accounts for 2 separate factors, human and ecological. This is where ozone serves as a protective function, and thus its depletion exposes us and the Earth to more radiation. The standardized unit of trichlorofluoromethane is representative of chlorine and bromine atoms that, released often via anthropogenic means, can cause the breakdown of ozone. Cobalt-60 is a radioactive isotope that can cause measurable levels of radiation poisoning, and becquerels are a measure of that radioactivity. Eutrophication is the process by which excess nutrients in water lead to algal blooms, which compete out oxygen for fish and other aquatic species. Phosphorus, along with nitrogen, often found in fertilizer runoff, are major contributors to this process. Now, all of these factors are to an extent regionally dependent, and water is especially so. If using water in an area where it's already scarce, this can have more damaging effects. Human activities that lead to nitric oxide, ammonia, and sulfur dioxide emissions contribute to increased soil acidity. This factor considers land that is transformed for human use and the time occupied separately. For instance, a construction site might use land that has already been transformed from its natural ecosystem, in which case the transformation cost should theoretically not be applied. But here I wonder if it should, since it's land that is being prevented from returning to its natural state. And finally, okay, so these 18 factors give us specific measurable results, but how do we interpret them? Can we aggregate them into broader categories that give us easier way to compare products? The answer is yes. The ReCiPe methodology defines these 18 factors as midpoint factors. Now, did you notice any themes pop up as we went along? The themes I referred to relate to what are known as endpoint factors. The midpoint factors translated into 3 endpoint factors: impact on human health, impact on ecosystem quality, and impact on resource scarcity. These translations take effect via a damage pathway. For instance, we can take the midpoint factor of freshwater ecotoxicity, which would be measured in somewhat objective terms in terms of the kilograms of dichlorobenzene produced, and then through its negative effect on freshwater species, we can return this value as the overall damage it causes to freshwater ecosystems when combined with other factors such as global warming and water use. Then we can aggregate the effects of a product's life cycle to include damage to terrestrial and marine species as well, in order to get an overall idea of how one product has an effect on the endpoint of ecosystem quality. There is a trade-off when making the conversion from mid to endpoint factors though. With midpoint factors, I can, with relative ease and fewer assumptions, compare the freshwater ecotoxicity of 2 different products, plastic and glass. However, comparing 2 products only from this one factor may miss out on the bigger environmental impact. Alternatively, I can generalize the product's impact on large areas of the environment, such as ecosystem quality. But that comes at the cost of an increasing number of assumptions used in the data translation. In other words, the results from midpoint factors may be more accurate but reveal less about a product's overall impact, while the results from the translated endpoint factors give us a better overall picture of the product's impact. This comes at the cost of increasing our certainty of the data. ReCiPe2016 offers one methodology for life cycle impact assessment, but it's not the only methodology available. My goal with this research was not to comprehensively outline each methodology, their strengths and weaknesses, or how to perform them. Rather, the intended audience is non-specialists like you and I. And the goal is to give a better understanding of the many factors that can go into determining a product's sustainability. That being said, I do think the strengths and weaknesses mentioned in the ReCiPe 2016 article do shed further light on improvements that can be made in determining environmental sustainability. Controversial topics such as pesticide use, infectious disease incidents related to climate change, invasive marine species, and plastic debris in oceans were unfortunately not included in the 2016 update to ReCiPe. It is likely, however, given the importance of these topics and their impact on environmental sustainability, that future versions of ReCiPe and other methodologies will consider these impact factors as more information on how to assess them becomes available. Also, given the advancement of science and technology, other topics will continue to develop that affect sustainability. Those mentioned in this article include issues such as noise pollution and nanoparticle use. I'll leave you with some food for thought. Why is it that we separate ourselves from the natural ecosystem? What I'm getting at is why this methodology has created a separate endpoint factor for human health, distinct from ecosystem health. Are we not part of the ecosystem? Personally, I don't think this is an issue with the developers of ReCiPe, but rather something inherent within our thinking. Because it's likely you didn't think twice about the fact that human health was separated. I know I didn't. Let me know in the comments your thoughts. Until next time. Becquerels, the standardized unit of chlorofluorocarbon is, damn it.